An 89-kilogram box slides 31 meters slowly at a constant speed down an incline of 25 degrees from the horizontal by a man pushing fully against the front of the box to stop it accelerating. Assume that the friction is negligible. What is the force exerted by man on the box? What is the work done by gravity on the box? What is the work done by the man on the box? What is the net work done on the box? Okay, so to start this off, we'll always have to draw a diagram, so let's do a diagram of this. So here's our incline. We're told that the angle of the incline is 25 degrees. So here's our box. It's traveling a distance of 31 meters, constant speed. This is our guy who's pushing against the box to make sure it doesn't accelerate down, so he's pushing against it. We're told that the mass of the box is 89 kilograms. And I think that's everything, right? So the distance is d is 31 meters. Assume the friction is negligible. I think that fully covers everything. Okay. So a free body diagram tells us there's a force of gravity on the box. There's a normal force. And there's a force that the guy is pushing. Let's call it FP. And then there's a parallel component. So that's basically three forces acting on the box. Okay, so there's only three forces acting on the box. But if I look at the incline, the force of gravity is acting down. And there's a parallel component of force, which I'll call it as F parallel. That's going along the incline. The component of this force, of course, of gravity along the incline. And there is a Gn for the normal force that's going perpendicular to the surface. So the gravitational component of force that's acting down, which is this way. And I know that this is a right-handed triangle, and if you think about it carefully, you'll see that this angle theta must be the same as this angle theta. So the parallel component of force is equal to Fg sine of theta, which is equal to mg sine of theta. The guy is moving, he's holding back the box from accelerating, so he's pushing up this way, so F push. So that must be equal to the F push, the magnitude of the pushing force that he's applying. So F push is equal to mg, the mass is 89. Gravitational acceleration is 9.8 meters per second squared. Sine of 25 degrees. And let's bring out our calculator. So 89 multiplied by 9.8 times 25 sine. I have 3.7 times 10 squared newtons. So the force that the guy pushes is 3 times 7 times 10 squared newtons. Now the work done, what is the work done by gravity? So work done by gravity, so if you look at it, so F parallel is the work, gravity, parallel force that's going down. The displacement happens to be in the same direction. So this is going to be F parallel dotted with the displacement in the same direction, so this becomes F parallel times D cosine of, the angle between them is 0 degrees, so this is just F parallel times D. So the work done by gravity is going to be 3.7 times 10. Actually, let me put the equation in. So instead of just putting numbers in, because I prefer if you didn't put numbers in equations until the final step. So F parallel is equal to Fg sine theta, which is mg sine of theta times d. So it's mg d sine theta. So the mass happens to be 89 times 9.8 times sine of 25 degrees. Is it 25 degrees? Yeah, sine 25 degrees times a distance traveled of 31 meters. So let's plug it in now. So I could have actually done 3.7, but I wanted you to actually see the equation. Okay, so 3.89 multiplied by 9.8 multiplied by 25 sine multiplied by 31 equals, so 11427 joules of energy, which we rounded off to two significant digits, which is 1.1 times 10, 1234 joules of energy. So this is the work done by gravity. Okay, work done by gravity. What is the work done by the man in the box? Okay, actually, is there space at the bottom? I think so. There's enough space. So if you look at it, so remember, he's pushing in the opposite direction with the same parallel force, but he's pushing in the opposite direction. His balance is F parallel with the F push force that he's pushing. And the angle between them so the work done is going to be F, the push vector, times the displacement vector. But remember, Fp times d cosine of, the angle between them is 180 degrees. And cosine of 180 degrees is minus 1, so FPD minus, which is minus F parallel times the displacement. And we already calculated F parallel times displacement. Cosine 0 is 1, right? So remember, this is F parallel times D. So this is going to be equal to negative 1.1 times 10 to the 4 joules. This is the guy pushing, PP, WP, WP. And what's the total work done by, this is the work done by the man on the box, which is negative 1.1 times 10 to the 4 joules. And what's the total work done on the box? The total work is equal to WG plus WP, and they both cancel each other to get 0. So total work on the box happens to be 0.